Hello, good evening everyone. My screen is visible.
Yes, ma'am, is good.
Good evening everyone. Welcome to today's section, Course System Design through Verilog, Week 7 Test Benches. So first we will start with the combinational circuit example and the test test benches for the combinational circuit. So test benches is a program to verify the correctness of a hardware model. So it is we usually write the test bench in the very low. Okay. And these test benches are not usually synthesizable. Keywords like initial. So these are not synthesizable. So synthesizable means we will be not able to convert them to the hardware. Um, so here let us consider the design and the test. This is our design and the test. DU. So this is our Verilog module, and we will be applying the inputs to the test bench. So we will be like, generating inputs to DUT, and we will be getting the output. So we will be performing checking output of DUT. This and this we will be performing through test bench. And then when we are applying an input, we need to store. This is like we are applying the input to the DUT, so we need to store it. So it should be a register type variable, and we are getting an output. So we are like driving it continuously. So it will be a wire type variable. So this is a synthesizable mm, Verilog code, Verilog or VHDL. So synthesizable. This will be a synthesizable circuit. And this circuit's functionality we are going to check. Functionality. So how we are going to implement the test benches? Test bench will be like module and then module name. So its syntax is module and then the name of the module and directly semicolon. So there is no fault declaration. And also like next we will define the input with the keyword register. We will define all the input ports because we need to store the value and apply to the DUT. And then wire we will be used to drive the output ports. So these are the there is no port in the declaration of the module and register for the input and the wire declaration. So you so we are using two different type of signals for driving. This is slick driving, and then monitoring output during the simulation. So this is purely for the simulation purpose. This test bench will not be converted into the hardware. And the register data type, this for assigning this value, it should be inside a procedural block. So it should be either inside always or initial. So it's non-synthesizable, so we can use initial also to initialize the values. And then wire type, this is a physical connection. So we cannot use initial or always block to assign it. So this wire has to be assigned to assign statement only. Okay. The next, the purpose of test bench is to verify the design under test module whether it is functioning correctly or not. So this is the general syntax. So we have module, module name, end with semicolon. There is no port list. And then we have to declare the register and wire. So for register, input ports, wire, output ports. And then we have to instantiate our design under test and pass all the values, all the test signals, all the this one and this one, our input and output ports. So we will have dot here. This value will be same as the value in the module, followed by we will apply a signal here. This value will be same as in the test bench. And then we can display it. We can also print it or use some dollar monitor. And then to stop or finish, dollar stop and dollar finish. Two statements can be this way. And then end module. So now let us try some example. First we will write the Verilog code for the AND gate. So it will be start with module name AND gate. So let us write it in behavioral only. Output port behavioral, so register type variable y input a comma b, and then always at the rate of a or b whenever any input a or b changes. Begin. So you know that any one of the input is 0, output is 0, and when both a is equal to 1 tick b1 and b equal to 1 tick b1, again y output is assigned to 1 and then begin n. So and then else y is equal to 1 tick b0 and this is for this side and this is for this end. Okay. Then end the module. For this Verilog code, let us write the test bench. So first we will start with the module and the test bench module name. So and to let's say test bench and no port declaration, so semicolon. And this also will end with end module. Then we have to declare this port input. It will be register. The name can be same or different, followed by output wire y. Now we have to call this block instantiation. This so name of the module and then instantiation name. Then this you can pass in two ways. First is first value output. So positionally I can keep y and then a and then B. Or else I can use a dot operator Y and then uh, Y comma with the name. I can pass the values to be given under test. So okay, I will use the dot Y is connected, should be connected. Dot A should be connected. Dot B should be connected. So this is our instantiation. Then next, I want to initialize once. So this values I wish to apply only once. So initial begin. It will start at t equal to 0. So first is A equal to 0, B equal to 0. So this value will be applied at t equal to 0. And then say I apply all the combination A equal to 0, B equal to 1, A equal to 1, B is equal to 0, A equal to 1, B is equal to 1, hash 1. This is for delay. And then this is the test bench code. We have written this in Verilog. And we have one begin, so we need one end. And then end value. Okay. Similarly, let us try for the multiplexer. So let us take 2 cross 1 nodes. Cross 1 nodes have 2 inputs y0, y1. Let us say y0, y1. And then output delay and one select line. Okay. And select 0, select y0, and one select complement I0 plus select I1. Okay. So now we will write the Verilog code. So this Verilog code we have already discussed. Model marks select I0, I1, and then so now we have to declare this as which are input codes and then which are output codes. So output out. We want say we use behavioral modeling. We want another register to store it. You can take a register always at any one of the input changes. So if you want to write select or I0 or I1. As we are mentioning everything, I can directly denote asterisk also. So begin. I want out register is equal to select. We'll write the equation and I0 or select and I1 and then end. Then I will assign this to the final out underscore reg end model. So now let us write the test bench for this. So here I will discuss as time scale. Time scale. So usually when we were saying this one hash 5, we were saying it as delay and we were mentioning it as 5 unit. So now if we want to define it like what is this unit, whether it is 1 nanosecond or 10 nanosecond, we will be using the time scale. Pick time scale. And this will be like 1 nanosecond, 1 picosecond. This is for precision. So like after every one pico, it should be able to detect. It should be like precision. So if it is 1 picosecond, so it will detect 1 pico, it will detect 2 pico, but if you give 1.5 pico, this it won't be able to detect. And then module test bench. No ports, and then now info ports followed by wire output port, and then instantiation of the module. The mux instantiation in M1. Now I will pass it directly. Okay, so I have select. Here first I have to pass select, then I0, then I1, and then out. Then again initial begin. So some delay of 10 nanoseconds. Select is equal to 0, I0 is equal to 0, I1 is equal to 0. So at 10, I'm defining everything to be 0. Then after some delay, I'm changing this to 1. I0 is equal to 0, I1 is equal to 1. Now carry will be daily. And then carry as DNB or DNC or yeah. So it's one and test bench for this. Model. This is the test bench. So I can also write the variable name as test bench and then register A, B, C are the inputs. Outputs are sum and carry. So now I have to instantiate this block F A. This run the test. Then I can pass A, B, C and then carry. So when you are passing directly, the order should be same as the order in the module. Initial, begin. Again, you can write pass some values. A is equal to 0, B is equal to 0, C is equal to 0. This is 1 bit, so I'm writing 0. Or else you can write 1 tick B 0. For more than 1 bit, we will be using this way of writing. And then after 10 nano, if I want to stop this simulation, I will use $stop and model. This is the writing of the disturbance for the combination of circuits. Some of the disturbances and some portion we have already discussed in the previous classes when we were trying to simulate them in the EVFA. The sequential circuit for D flip flop. So this is the D flip flop. D is the input, clock is another input, and if we are using reset, this is another input. Q is the output. We can also have Q bar if we in this way, we are in this code we are using only Q. Then so D is the input and then D Q reset are the inputs, Q is the output. And at the positive edge of the clock, whenever it is a positive edge of the clock, at this edge, if my reset is equal to 1, my Q will be 0. Else, my Q will be equal to V. This is they have written. If the reset is 1, Q is 0, else Q is equal to the D. And then in the module. So for this Verilog, let us write the test bench. Here you can define the times here according to your needs, and then module is D flip flops test bench. And then inputs are register, clock, D, and then reset. So if I want to use some other word, like some other keywords, RST for reset and CK for clock. Now wire output is say here it is capital, I will write a small q. Then now I will instantiate. Verilog is a case sensitive language. So now first is q. Dot q is applied to this q. D is applied to D. And then CLK is CK here. And reset is RST here. Now inside the initial begin, I want to initialize the inputs. So D is equal to 1 tick B 0. Clock is equal to 0 initially. 1 tick B 0 and reset. Okay, our clock is CK here. And then our reset is RST. 1 tick D B1. This will be at T is equal to 0. So then after some delay, just change the reset to 0 and then forever 40 D is equal to 0. So what I am trying to do is we are having okay, first I let me generate the clock also. Always hash the clock is CK. CK is equal to and module. So forever will be like running continuously, like while one. And this forever should be inside either an always block or inside an initial block. So it's inside the initial block. Initial begin, it is ending here. And this I trying to say D is and then this is equal. So for 10 it was 0. At 20 it went to 1. Again at till 30 it will be 0. Again it will go to 1. Again 40 it will come. So after every 10 nanosecond it will be toggling. So the one clock period will be 20 units. And then D, for 40 it will be initially it is 0. So till 40 it will be 0. After that it will go to 1. Again after 40, that is 80, it will again come to 0. This way it will be keep on changing. So this is D is equal to D complement continuously after every 40 delay of 40.
Ma'am, please explain this diagram, ma'am. What you tell?
This clock waveform,
Yes, ma'am.
yes. So first initially let us draw the clock. Clock is 0 at time t equal to 0. So at 0 it is 0. At t equal to after 10 delay, it should go to clock bar. So it will go to logic 1 at 10. Again it will should complement after 10, 20 it will complement. Again 30 it will go to 1 complement. Again at 40 it will complement. And this will be repeating. Whereas my D input, it is initially 0. It will be 0 till 40. When in 40 units of time, here it will be again complementing. This will be keep on going till 80. 40 plus again 40. After that it will come to 0. So this will be like changing at 40, 80, 120 in that way. Mm,
Okay, ma'am. I
so
understand. Ma'am,
next,
if we have taken, excuse me, ma'am.
sorry,
Ma'am, if we have taken time scale for the 2 nanoseconds, how it will be affected for the clock cycle? Yes.
like 2 nanosecond per 1 picosecond.
Yes.
This 1 picosecond, we can like detect at the precision of 1 picosecond. So at 1, if we have a signal of 1 picosecond, we can detect. If we have say 2 picosecond, we can detect. But if it is 1.5 picosecond, then this change will not be detected.
Okay, but the time scale unit here for the 10, 20, 30 for the clock, will it be changed?
Yes. Now we are saying that 1 nano, so unit we are saying as 1, like this has 10 nanosecond. If we say like this, then it will be 20 nanosecond.
Okay.
We will take one example of finite state machine. Um, I'm directly giving the state diagram. So it is 0, 1, 0. So this is a relay machine. So every input there will be an output. Model, FSM. This relay FSM, right, we are having some shift registers. That is the flip-flop, some memory element. This we will have it one plus. From this we will obtain some the final output. This will have some combinational logic. And for the input, we will have some next step combinational logic. So to this we will have some inputs and then the memory element. This will be our more machine. But if I am having a million machine, the output will also depend on the input. Output will also be a function of the state as well as the next state as well as the input. And then this is the output. This is a relay type machine. This is easy to design and lesser complex, but output is depending on the input. So any change in the input will cause the change in the output. So there will be some glitches. So for give the code directly, so say module, you know the syntax, the name, and then the port list. And this will bring the part of the code, and then you will define the register, which is the state, and then next state logic, and then some, and then uh, parameters for the state. S0 is equal to 2 things will be 0, 0. S1 is equal to, so you have to initialize all the states.
Excuse me, ma'am.
Yes.
Not visible.
Huh?
Not visible, ma'am. What to write? Yes, now. Now I can see.
Now it is fine.
Yes, ma'am.
Yes. And then S2, 2 will be 1, 0. S3, 2 will be 1. Actually, guys, at the pause example block, the negative edge of place set. So this is negative edge. That means this edge. Active, low. And then if reset equal to 0, active low, my state will be S0, the initial state. Else my state will be equal to next state. And then this always block, I have not written begin and end. So after this one statement, the next statement I will write inside the another always block, always at the changes of the state or with the changes in the Excel case state. So S0 if X of int, if it is 1, it should go to 0, 1 state, S1 state. This is S1, S0, S2, S3. It should go to S1, otherwise S0. My next state will be S1, else my next state will be S0. The same way you can write for S1, S2, and then S3. And like my you are in two state. What will be the next state? you are in S1. If it is 0, you are at 0. 1 means 3. So S3, S0. So same way S0, S2, you can write for all the states. S2, and then it's 0. And then we have to assign. Okay. So if it is in S0 state, y out is equal to 0. It's initial state. Then S1, S2, S3. My output will depend on state as well as on the X, the input. So in case in model. So this is a Verilog course for the relay FSM, one of the state. One of the state transition FSM diagram. So this is an example of a zero detector. So now test bench. So as a model test bench. Then what is the this can be different for also. Then in now this now instantiation. I have used just a name, so I will write this as Verilog, DUT, then TY output, then input. T, this is X, test bench input, and then TCLK, and then TRSK. So initial, then I want to terminate the simulation after 20 milliseconds. So I write initial, and then after 20 minutes of time, finish. Then I want to find it times it's a 20 time minutes. Now I will initialize the values. Initial begin the clock is equal to 0. My clock should toggle forever for after every units of time. Yeah. Here I have given it. Forever is inside this initial block. Now, say if I want to assign some values, I want to execute parallelly. So I will use initial, forward, and then join. At equal to 0, test events RST equal to 0. At 2, test events RST equal to 0. Now I can define some values. 87, TRST equal to 0, 89, TRST equal to 1. So previously when we were like defining this inside the always block alone without the fork and join, That time we were saying like $2, $2. If there are two statements, then we said this will be at 2 units. This was at 4 units when this was inside the initial block. Okay. Now, when I am writing this inside the initial fork and join, and I am writing, say, I will write this as a 3, then this was at 5 units of time. Now, if I have 2 and then 3, this will be executed at 2 unit of time. This will be at 3 unit of time. All the execution will be in parallel. And say if you have at $2 and $2, mostly it is like it will be taking the second value. Or it depends on the simulator and the version of the Verilog. So you can define some inputs. Then ending it like it syntax is fork and then join. It should be inside the initial. Here you can have the values which you want to execute parallelly. Any doubts?
One more time explain.
Yes. So in the testament, wire, these are my output port and input is key exchange, clock and the reset. Now I am passing it at like, positionally. First it was output followed by the input and then clock and reset. If I change the position, I will be using the dot operator. With variable name in test bench can be different. After 200 units of time, I want to complete this simulation. I want to terminate the simulation. Initial begin, initially I am assigning clock to be 0. And then forever, I am making the clock to be toggle at 5 units of time. Forever should be inside the initial and begin initial block. So
And forever is a keyword.
forever is a keyword.
Okay.
Forever is a keyword and it will be like first initial to a 0. After 5 units, this clock will be like toggling. 5, 15, 20. It will be toggling. And we have to use for whenever you are using a forever, it is like while one. Like it will be continuously executed. It should be inside the initial block. The like statement which you want to execute continuously, and then this is the syntax of forever. And same way, fork and join is to execute these statements in parallel. Like if I write inside directly initial block, if I say #2, #3 delay of 2 units, 2 plus 3 delay of 5 units, this statement will be executed. But whereas if I use initial fork and join instead of initial begin and end, inside the initial fork and join, this will be executed at 2 unit, this will be executed at 3 unit because all our execution of all the statement will start at the same time, like parallel execution.
Okay, ma'am.
So next is so this is Mealy machine. So whenever input is changing, the output will change. So in the Mealy machine, we will have some glitches. Output changes when input, not only when, like also when input changes. So next we will discuss the processor. So any processor we will have the arithmetic logical unit, ALU. It will be controlled by the control unit, like which operation has to be performed. And then output, it will get the operands from input or from the memory. It can store the operand to the memory and get the input operands from the memory. So now, like, if this is my ALU, this will be the output. Based on the output, it has to perform the operation on two inputs, A and B. And then we can have two more flag signals, carry, flag, and then zero flag. So my ALU, which is the 8-bit, will have a result. If you multiply two 8-bit number, 16-bit will be the output. So 16-bit let us have. And then we will have a flag, two flags, flag C and then flag Z. And then three inputs, operand, opcode, to choose which, output 2 down to 0, and then operand 1, operand 2. And then now let us define the output and its corresponding operation. Say first 0, 0, 0, I wish to perform addition. 0, 0, 1, subtraction. 0, 1, 0, multiplication. So these three arithmetic operations. And operation 1 operation some logical operators. So these are all logical operators. So based on this opcode received, we have to decide like which type of operation need to be performed. So with this, we will proceed with the Verilog module ALU 8-bit. So inputs are, I will define here itself. Output, operand 1, operand 2. And then final result. Also we have two flags, flag C, flag Z. Now we have to define input. Output is a 3-bit value, and then operand 1 and 2 are 8-bit values. Operand 1, operand 2. And then result, we are already discussed. Output result, which is a 16-bit value and a register. Register 15 down to 0, and then result. I can initialize this to be 0 initially, then output register flag C, which is also 0, and flag B, one tick be 0. Now we need to define the parameters. This everything will be decided, saved as a parameter. Parameter add will be 000 add, a sub will be 001. So this we will define it with parameter. This is a 3-bit. I will use everything capital because small and small are all keywords. So 3 take me 000. My sub is 3 take me 0 0 3. All equals 0 1 0. I think we can always count. So 3 take me 0 1 0. So in the same way, the other operators. Next, whenever the output changes or two operand changes, these are only the 3 inputs. So I can write star also. Or operand 1 or operand 2 or 4. Okay, result is output. If it is an say add, we have to perform addition. Result will be operand 1 plus operand 2. And the same way flags. For subtraction, we get result is equal to operand 1 minus operand 2. And then same way. For the other multiplication and operation, we have also or we have land nor or default. If it receives some other input other than this, then it will go to the default value where you can initialize result equal to 0, flag C is equal to 0, flag Z is equal to 0. This is for this, then end case, end for this always block, and then end block. So in this way, you can write the Verilog for the 8-bit ALU. If you want to write text bench for this, some time scale you can define as non-NSA as per the requirement and module the ALU test bench. After inputs of output and output. and then output is a 16-bit result and the class C flags. If you want to like have some counter, you can also define additional variables required. But ALU, variable design under test. First output, second operand one. You can say here output operand one, operand two, result flag C, flag D. Operand one, operand two, result flag C, flag D. Now initial begin output is equal to
Ma'am, DUT means
it's our own user defined name. So I am writing for just to stay short form of design under test.
okay, ma'am.
This is our own user defined name. You can write any name just for reference. And then opcode 3 tick B0, operand 1, 8 tick. So if it is B0, operand 2, 8 tick B0, and then begin after some delay. The operand 1 is changed into 8 tick HAA and operand 2 is changed into 5. Now with these two operands, we wish to perform all the operations. So the opcode should be from 0000 to 111. So instead of writing it with a delay and everything, we can write inside a for loop for the count equal to 0 to count till 3 tick be 8. Count is equal to count plus 1. 1 tick b1. Then begin and then end. Already one end begin is open, so end and then end model. So now I wish to have opcode from 0 to 8. So my opcode is equal to count. And there should be some delay. So in this way you can use some for loops to obtain all the combinations. Any doubts in this? So this for loop syntax is same. In C we will use this instead of this curly flower brackets, begin and end we are using it. Any doubts? So first let us start the read operation for a register file. Next in the ALU we have some register files. So now will be repeated how many times? So loop will be 0, then increment count plus 1, so 1. This is also lesser than 8, so it will execute 2, till 7. If it is equal to 8, then it will come out of the loop. This is our opcodes. So in this way, we can perform all the opcode operations given by the opcode on these two operators. Clear? Any doubts? So this loop will be executed 8 times from 0 to 7. Opcode values will range from 0 to 7. Any other doubts? So the read operation, we will have multiple like register files. Say register 0, register 1, and minus 1. If minus 16, then this will be 15, 0. And say each register can hold a 32-bit value. Then I will be getting like this 32-bit value. So usually we will represent the width with this notation. We have to select one from this, and this will be our operand 1. So like for any operation we need 2 operands, right? So another operand, we need another multiplexer. So this will be our second. Now we have to select between this. So there are total between 16 we have to select. So we need 4-bit selection. Select 0 to select operand 1. To select operand 2, select operand 2. This will also be a 4-bit value. So this complete block is our register file. And then this operand we will be applying to this ALU based on the opcode. We will get the output. This is for the read operation. So if now for we wish to write into this register files, for writing the architecture will be write 0, like register 0, register 1. Yes. Yes, you can unmute and then ask. Now tell me one example related to comparator. Comparator. So here you are using if statement anywhere. Here we are saying if equal to 1. This is a comparator. Like some comparator. I hope you are asking this only, right? Comparator is this one, equal to less than greater than. So here we have used equal to comparison, and then similar like here when we were using for loop, we used less than comparison. I hope your doubt is cleared. Any other doubts? I think someone raised your hand. Maybe you can unmute and then speak. If no doubts means let us proceed. The same register n minus 1. So it is from 0 to 15. Now we have to enable this register. So we need one enable signal and this will be enabled if we are going to perform the write operation. And then we will have a decoder. It will be right here. 0, 1, n minus 1. This is our decoder. So we will have a 4-bit select input. So when writing, we will write the input to one of the register. Now we have to write this. We are selecting this register by using the decoder. And now we have to write this input. This will be a 32-bit input. This will be 32-bit input. So this entire block is our register file. And for like our logic, let us consider this to be an active high enable signal. Similarly, this also we need to like enable when with respect to the read signal RD. If it is 0, then we will not be performing the read operation. So now coming to the Verilog code. Before Verilog code, let us draw the block. The register 5 will have two outputs as the output. Output 1, 3 down, 31 down to 0, and then output 2, 31 down to 0. And then inputs are IP1, which is also 32-bit. And then select I1 for writing the input 4-bit, and select for output 1, this is 4-bit, and then select output 2 4-bit, and then clock enable read signal, write signal, and then reset. So this is the all the input and the output blocks. All these are 1 bit. Okay. Now coming to the Verilog side. Module. Name of the module register type. IP1. You can write all the port list. Input 31 down. The same way you can define all the input and output. And then we want to have some signed and unsigned numbers, so you can use some integer i. Integer i. I have one skip enable and meaning this. Just instead of saying it as over in the always block, we can directly write here. So now always at the rate of pass SEO begin if enable is equal to 1 and if it is reset, we have to reset all the 16 32-bit registers. So begin. Now we will use a for loop. For I is equal to 0, I less than 16, I plus I plus plus for equivalent is I is equal to I plus 1. This one will be 1 tick B 1. Begin this register file of I will be initialized to 30 end. And then otherwise this. And then this one we don't know the OP1 and OP2 value. Once after the read operation only it should be a specific value. So it is don't care. And then end. Then if it is not the reset. So if RST not equal to 0, then it is not the reset. So begin. Now we have to check between read and then write operation. So to take B00 begin. So 00 both are not selected, so we can leave. And then 01 the register 5 of this I1 is assigned to IP1. 10 this is begin, and then OP1 is this address will be in the select 01. For OP2 this address will be in the select 02. Now if it is both read and write, now if we want to perform both read and write, both the statements will be we have to write. So the OP1 this one, and then OP2 also at the register file of the selected one, select I1, Ishwara. So this is end case. So you can end all the blocks and then end module. So this is our register file. 101 is read. So we have read. From the address cell 0 select 01 and 02. And then 01 it is for write operation. So at the I1 address I am writing the IP1. This is just to see. It is like when you want to sign number, you can also enter that. If we proceed for that text event, um, time scale 1 nanosecond per picosecond. Register file. It is the text event. Register. You can define all the input and output and then wire output and then instantiation. Next file DUT port list. All the input and output values initialization. Then initial begin IP1 is equal to 32 Same way you can initialize all the values. Then after after completing this initialization, the other sequence I said you can make it to 0. So here you need reset to the 1. And other the values which goes to this also. And then here we need clock will be 0. So we need to define this clock also. So we will have always begin clock is equal to clock 1. End. This is our Verilog code. So here you can define required inputs. Any doubts?
Excuse me, ma'am.
Yes.
Ma'am, I have got to go. Where can we get these recordings for this class?
This one we will be uploading in the YouTube and sharing the link in the log sheet.
Okay, that log sheet, when will you provide?
I think it is already provided to you, right?
Oh,
All the
sorry, this is the first session I'm joining.
okay. Some log sheet will be shared with you in the beginning, I think so. In that we are like this one. In this sheet we are uploading the link and the slides link.
Okay, could you please copy paste that link in the chat?
No, link I after uploading only I can share.
Okay, ma'am. The previous sessions I can see because
Okay.
I, yeah.
In the same link only, like same channel only you will be getting. I will
Okay, ma'am.
in the chat box. Yes.
Thank you, ma'am.
Yes, welcome. So next we will discuss the static RAM. So RAM is static and dynamic. Dynamic RAM like needs refreshing circuits. So those things. So that is, and then in this lecture, we will be discussing the static RAM. So we we need address line. These are the we need the address line, and then we need the data line, and then either chip select, read, and then write. This also we are taking as active high, generally active low, but let us assume to be active high, no more. So it is from 0 to 255. So n will be 8. 2 to the power 8 will be 256. So memory size is 256 bytes. So that means each is 8 bits. So with this, let us write a Verilog code. So the module synchronous static RAM. We need one data input, the data output, and then the address lines, and then the chip select write enable is WE, and then the write, and then clock. So now we need to define the bits. Let us define using the parameter. So my address is 8. So if I define it as parameter, now next time in the code I can directly use ADR to refer to 8. So if I want to change it to 16 bit, here I can directly change it to 16. That is the advantage of using this parameter. Parameter define my data in should be 7 bit, 7 down to 0, 8 bit. So DAT minus 1 down to 0. My output is a register type output variable, and then DAT minus 1 down to 0, that is data. My address lines are 32 bit. So address lines are also 8 bit. We need an n is 8, so 8 bit address line. So input ADR minus 1 down to 0. Then next, all the 1 bit input are the clock, chip enable, write, and then read. And then we need DAT minus 1 down to 0. We need such 255. If we say this is, you can either define it as this defect, and then always cos x clock begin if my C is equal to 1 and say write operation. That means my W is equal to 1 and RD is equal to 0. So this statement you have to write. That time in that my it is write operation. So to the SRAM that address, I will be writing the data. Else, if it is read operation, that means my RD equal to 1 and WE is equal to 0. Then to the data out, whichever is in this address from SRAM will be output. So with this will be end module. So this will be the static SRAM Verilog code. Yes, please. The test bench. So module test bench. Same way. You have to define all the register, wire, and the instantiation. Sorry. Synchronous SRAM. No, my module name is SY SRAM. SY SRAM. And then data in, data out, address, CS, WE, RD, clock. Now we can apply the different values. Initial, begin. So a set of values you can first begin with assigning to 0 of the values. Then you can wait for some 100 nanoseconds. Then apply the stimulus. Say WE, WE is 1, RD is 0. After 20, similarly. So you can first write something to the memory and then read something from it. So this that part is the same. Then to this we have here. So we are already in this right portion. So we can write delta m is equal to m x 12 at the address 8h4. Next I can read from this. So WE is equal to 0, RD is equal to 1. Now I can read it from 8h4. So in this way, we can write this distance and then end modules. This is the rough syntax for the test match. The next important circuit is the digital filter. So it is a frequency selective network. There are two types, FIR and IIR. IIR is infinite impulse response and FIR is finite impulse response. So if we consider say 3-tap FIR filter, then my output y of n is a x of n plus v x of n minus 1 plus c x of n minus 2. So these are the tap values. I have to multiply with a, with b, with c. And then this result we have to add. This result we have to add this will be the final y of n. Now we have to apply the input. Input is delayed version. So, n. So this we already discussed the ripple carry adder. We have already discussed the D flip flop to generate x of n minus 1 and x of n minus 2. Let us discuss another type of a multiplier called Brand multiplier. So this circuit, 3-tap FIR filter requires 3 multiplier and then 2 adder. This is a type of one of the multiplier which is used for unsigned multiplication, and for an n cross n multiplication. Yes,
Diagram explain previous diagram.
this one.
Yes, ma'am.
Okay. First is a x of n we want. So this is multiplied with a, input is x of n. Next is added with b x of n minus 1. So we need a delay element and we obtain x of n minus 1, which is multiplied with b, and we have to add both of this. Further, c x of n minus 2. So we need another delay element. We get x of n minus 2, and then we have to multiply by c, and it is added. This is the final output.
Okay, ma'am.
So for this multiplication, n cross n multiplier, we need n into n minus 1 full adder. So for say n is equal to 8, we need 8 into 8 minus 1, which is 56 full adders. The partial products, we will be partial products, we will be generating using the AND gate, like A0, 0, A0 into B0. Like this. And then, so we need 8 cross 8 is equal to 64 AND gates. If we have a block, we will get a sum after the addition. This carry is added with the next stage. So the carrier signals are shifted one bit to the left and are then added to the sum bit of the first adder, and the new partial product is like generated. And now let us just discuss this 8 cross 8 unsigned multiplication. A7, A6, A5, A4, A3, A2, A1, A0. B7, B6, 5, 4, 3, 2, 1, 0. These are the two numbers. So you will get A0, B0. This is the one of the like partial product which we will obtain from an AND gate. So A1, B0, A2, B0, A4, B0, A5, B0, A6, B0, A7, B0. Then A0, B1. A1 V1, A2 V1, A3 V1, A4 V1, A5 V1, A6 V1, A7 V1. This way we will get all the partial products. So we need 64 AND gates. A2 B2, A3 B2, A4 B2, A5 B2, A6 B2, A7 B2. This is 0. A0 B3, A1 B3, A2 B3, A3 B3, A4 B3, A5 B3, A6 B3, A7 B3, A0 B4, A1 B4, 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 6 B4, 7 B4, 8, sorry, something I missed. 0, 1, 2, 3, 4, 5, 6, 7. The same way, then I will get A7 B5, A7 B6, A7 B7. Only 3 rows, so let us fill it. A6 B5, A5 B5, A4 B4, sorry B5, A3 A2, B, B7. Final product terms will get here P15, P0 directly, P1, P2, P3, P4, P5, P6, P7, P8, P9, 11, 12, 14, 15. So this will be the LSB and this will be the MSB. So this will be generated using the AND gate. Then we have to apply this to and fill some half ladder or full ladder. This carry will be propagated here and the sum will be propagated here. So in this way, we can obtain the 8 cross 8 multiplication. It's an unsigned multiplier. So assuming that this code is already available, then module the FIR 3 tab filter, the input will be the clock xim h0, input will be clock 7 down to 0 xim, and then the other input 7 down to 0 h0 1 h1 h2 h0 h1 h2. These are the multiplication, and then output register 16.0 YI. Then we have to call this multiplier 3 times. Then we need add. So we have to call the 16-bit adder 2 times. And there are D flip-flop. 2 D flip-flop. DFF1, DFF2. So way you can write the code. Then finally sorry, I didn't get your question. Can you unmute yourself and ask the question? Yes, assignment 7 questions. We will discuss it. So the same way for the test bench, you know, we have to have the module name and then all the register wire and then instantiation initial begin and all the assignment put and then end. In this way you can like complete this test bench. Next let us proceed with some of the previous year assignment questions. So first question, for question 1 to 4, we are given with the 2x1 multiplexer module as well as the test bench. So let's proceed. At t equal to 0, what will be the value of S, A, B and then output is the question. So we know Y is S, B is to A and this is the initialization input. So at t equal to 0, these are the values. S is 1, A is 0, B is 1. When S is 1, it should select 2 input B. B is 1. So the output is 1, 0, 1, 1. Which is option D. Here. So now next at t equal to 5. This is at t equal to 10. So from t equal to 0 till t equal to 10, in this interval, my S will be 1, A will be 0, B will be 1. It will be selecting true, it is 1. So B is also 1. So Y is 1. So D will be the correct option. 1, 0, 1, 1 will be the answer. And the second question, third question, at the t is equal to 15 unit of time. So here t equal to 0, next will be 10, the next interval will be t equal to 20. So in this interval lies our t equal to 15. In this interval, which is 0, 10, 20, this value. So A equal to 1, B is equal to 0, S is equal to 0. So it is, will be selecting A input, which is nothing but 1. So S, A, B output.
One more time explain, ma'am.
At t equal to 0, we know S is 1, A is 0, B is 1. Is there any clock here? So there is no clock, direct assignment only. At t equal to 10, A is 1, B is 0. My S is still selecting 1. So Y will be, if I check at this instant, Y will be selecting B, so 0. At this instant, Y will be 1. At this instant, A is equal to 1, B is equal to 0, S is equal to 0. So Y will be A is 1. So the correct answer is S is equal to 1, A is equal to 1, B is equal to 0, and then output is equal to 0. Option B, 1100, because 15 unit will be somewhere here. So only this statement will be executed.
16, 7, t equal to 16, 17. That come means we can take t equal to 10 value.
Yes, in between till this it will be same. At t equal to 20 only value will change.
Okay, ma'am.
From 0 till 20, this will be the value. At t equal to 10, the value will change. And till t equal to 20, it will remain in the same value. The next question, again, t equal to 0, we know. T equal to 10, we know. T equal to 20, and then t is equal to 30. So somewhere here is t is equal to 25, so I have to evaluate this statement. So here 10, 10 plus 10, 20, 20 plus 10, 30. So at this point, my A value is 1, B value is 0, and S is 0. So I have to select S is 0 means A, Y is 1. So output is S, A, B, Y. I think I'm doing something not correct. Yeah, correct. 0, 1, 0, 1. S, A, B, and Y. Similarly, for the D flip flop and then corresponding uh, test bench, let us proceed. First, at t is equal to 18 nanosecond, my value of reset and Q is the question. So you can see from here, this is t equal to 13, 13 plus 18, and then this plus 37. So first 18 will be somewhere here. So till this I have to execute. So reset is 0 and D is 0. When reset is 0, output is D. So D is 0, reset is 0. So option A. The second question at T is equal to 35 nanoseconds. So now let's again see, we have to do this reset. What is Q? What is D? At the 35. 35 lies is somewhere here. So D is 1. Reset is still 0. D1 and clock is after every 10 nanosecond. So this is 10, 20, 30, 40. This is the clock. And then the D input is changing at 18. Somewhere here. D is going to 1 and remaining in 1. Sometime D is changing to 1 at 18. And 35 is the this point what will be the output. So it is at the negative edge of the clock, correct? So somewhere here is the negative edge. So this, if it is not sufficient, this won't be captured at this 20. Again, it has to wait till this edge for the Q to change. So if I see at this edge, it will be 0. So Q will be 0, D will be 0. Sorry, again option A. At 60 nanosecond, previously reset was 0. The D was 1 and that D at this 60 it will be 1. So Q will change to 1. So option B. The same way at the 68 nanosecond, you can see at this point reset is 1. My reset is 1. Still Q is 1. So 1. Okay. First turn is 1011. Second is 1011. D. Third is 1100. Option B. Fourth is 10101. Option C. And then fifth is 00. Sixth is 00. Seventh is 01. So option B. And eighth is 11. Any doubts? So put a please for a second and wait for a long time. Okay, we'll change to nanosecond. So here you can see there is some glitches effect because this is a Mealy model and it depends on the input changes. So in this way you can try running the codes. And simulate the SRAM circuit. Here I want nanosecond. So you can just see this. Initially, we were performing the write operation here. So this the data output was don't care. From here, we started performing the read operation, and we can see all the values. Okay. Uh, and in the register file, so here also you can see first at 0, 0 we are writing one value, at 0, 1 we are writing another value, and then here we are performing the read operation. RD is equal to 1. So in the read operation we are reading both operand 1 and operand 2. Here at 0, 0 this is the operand written, 0, 1 this is operand written. So both the location we are reading. So this is our register file. So any doubts?
Ma'am, please explain the reset and queue the value of question 5 to 8. It's very confusing.
5 to 8.
Yes, ma'am.
Yes.
You are going very fast.
Sorry. So at t is equal to 18 nanosecond is asked in the question. At that time, this is clear, right? We have values at 13, 31, and 38. So 18 will lie somewhere here. So these values I have to note. D equal to 0 and reset equal to 0. D equal to 0, reset equal to 0. Now let us draw the D. D is 0 from 0 unit itself. So there is no problem for the negative edge to see. So we can directly, I said, Q will be 0. So option A.
Okay, ma'am.
Okay. So the second question, we have to see at t is equal to 35 nanoseconds. And 31 only, D is 1. I think D is not 1 here also. It is in 31 only. If I draw the clock, clock is after every 10 it will toggle. 40, 50, 60. So this is clock. D input is 0 till, if you see, till this interval. So 31 only it is becoming 1. So 31 somewhere here, till then 0, then only it is getting to 1. So this is a negative edge, so every negative edge only it will toggle. So at this point, my Q will be 1. This is 40. So they are asked what will be the value of Q at this point when T is 35 nanosecond. So you can say Q is 0. So my Q is 0 and reset is 0. So option A. Now this is fine. I think in this
Yes,
system
ma'am.
I made a mistake. It should be from 41. And then this question at uh, 60 nanosecond. So there is no change at 60 nanosecond. Okay. So we can refer to this waveform. 60, it could have seen one neg and 1 second negative edge. So no problem. There is a change here. So here Q will be 1. So in this, the Q change will be reflected. D is in the previous value. Reset is 0. So it is 0, 1. Now it is clear?
Okay, ma'am.
Yes. At the eighth question, we have to see at 68 nanosecond. And at 68 nanosecond, reset is equal to 1. The value at D will be reflected at the negative edge of the clock. So 68, this will be 70. 68 will be somewhere here. At this edge, reset is 1. So D will be 0 only after this negative edge. So that of Q will not go to 0. Q will remain in 1, but reset will be changed to 1. So option D, 1, 1. Clear now?
Yes, ma'am.
Any doubts?
చిన్న వింటున్నారా
Any doubts?
ఇది రిపోర్ట్ రాలేదు ఇంకా
Now from question 5 to 8 it is clear, right? Sorry, I was
నేను
little
ఫోన్
fast.
చేయలేదు ఫోన్ చేయాలి
Yes, ma'am.
Clear.
చేద్దాం అనుకున్నప్పుడు
So if no
మీరు
doubts, we can
ఫోన్ చేసుకోవాలి
complete today's section. Thank you so
2 రోజులు
much.
పడతాను మరి రిపోర్ట్ అది ఇంకా రాలేదు
No doubts.
అయిపోయింది ఆఫీస్
Okay.
అయిపోయిందా
Thank you all.
సరే సరే ఓకే